One more talk before lunch. Lingsen Meng talking about application of seismic ray processing to earthquake early warning.
Hello, everyone. Thank you for staying to the last talk before lunch. So I'll try to be quick. I'm from UCLA, and in this talk, I'm going to present something a little bit different from all those finite fault solutions we've seen in the previous talks. So we're trying to apply this seismic array processing to earthquake early warning. And this is a project I actually started at the end of my PhD at Caltech. Then I carried on to Berkeley, where I did a postdoc with Richard last year. So this is a kind of a collaborative research, and I'm going to continue to do this at UCLA. So today, I think Nakamura-san earlier this morning talks about the performance of the EEW system for the Tohoku earthquake. And one of the key information is that using seismic approach only, that we tend to underestimate the magnitude. And this is a figure showing all the kinds of estimate, and it's saturated at 8.1. So it really tells us that there are limitations to the current earthquake early warning systems using only the point source assumptions. And on the right side, this is the comparison of the ground motions of the earthquake intensity of the predicted by the JMA or the actual ones. So you see, like, ignoring these finite dimensions, you underestimate the ground motions in the contour region. So we really need to have finite dimensions in the real-time system for earthquake early warning. And it's actually great to do this in the last talk, so I can sort of summarize the few approaches that people presented. So there are a number of approaches trying to do finite fault dimensions in real time, and mostly based on GPS. And there's one approach, the finder approach is based on seismics, and the others are based on GPS. So there's examples of the Tohoku earthquake by the Italian groups, and Ronnie present the GLARM systems based on network approach, and Sarah just did a presentation on the before system. So these are all kind of geodetic systems. So what I would like to add in this earthquake early warning arsenal is that we want to use the small array of seismometers as a radar tracking the rupture propagations in real time. Because as we know, like when the earthquake happens, the rupture tip or the rupture front is usually radiating a huge amount of high frequencies. And if we can track that as the earthquake grows, we can sort of map how large the fault is, and also trying to get the rupture directivity and maybe the rupture speed. So the idea would be if this is the fault planes, this is a Straxity fault planes, and this bright part is the rupture tip. And we have a small array relatively close to the fault, and it's going to keep tracking the direction where the high frequency waves comes from, and it's going to map the rupture length. And it would be better if we have a network of these small arrays located with kind of overlapping field of view, different coverage at different part of the fault. And we are thinking about building a system like this in active fault systems, such as the San Andreas fault. And the next step would be to validate the approach or demonstrate it with real data. But the truth is there isn't so many big enough earthquakes recorded by a relatively dense array close to the fault. And the closest example we have is the 2004 Parkfield Earthquake, where we have a kind of kilometer scale array with a dozen of sensors located about 10 kilometers away from this earthquake. So the idea would be, what would be a simple approach that we can use to track the ruptures and get the information we need for real-time earthquake early warning. So let me explain how this the figure works. So what we do is first that in the case we only have one array, we still have to assume the strike of the fault. Well, this is similar to the G-alarm system where Ronnie talks about. But I'm going to show that when we have multiple arrays that we can kind of release that assumption. But for this case, let's assume that the fault is parallel to the San Andreas fault. Then for each time instance, you would compute the cross-correlation coefficient between all pairs of stations, which depends on what are the direction that you're assuming the waves is coming from. And if then you average out all the cross-correlation coefficient, you get a single value, and that's the colors showing here. So this axis is time, and this is distance along the fault. The idea is at each time instance, the maximum cross-correlation should indicate where the rupture front is. And if you do this over the whole duration of the earthquake, you will see where the earthquake starts, and you will see where it ends. And that's going to give you a rupture length, as well as the rupture directivity, if you take the relative position of the rupture length with respect to the hypocenter. And that's what we are doing for the Parkfield earthquake. Of course, the reality is that there's always some complications. And the particular complications we encounter here is that the direction that you will get from the small array is not exactly, when you try to back project it on the fault, it's not exactly located as the true locations. So the 5 green dots, or the 6 green dots there are a few aftershocks where we're testing how accurate the back azimuth is. And the red ones are the locations we inferred from the array. So we see the back azimuth and we project it there. So you will see like the true locations, the green ones, tends to be biased kind of towards the center of the fault. So there's some bias there. And if we plot the true azimuth of a series of aftershocks in this area versus the bias, which is the observed azimuth minus the true azimuth, you will see it has a systematic trend. So it's not random errors. So what would be this error come from? So it turns out that in the nuclear monitoring community, this is a well-known problem. That is, if you have a deeping layer beneath the array, this deeping layer will kind of bend your azimuth estimate. And if you do this over the range of 360, well, for nuclear test band, they will be able to do this over the 2 pi range. You will see that this bias kind of have a cosine shape of pattern. And this is actually well known, and that cosine curve can be used to determine like what's the actual dip of the deeping layer, orientation dip. So here we only have a like 90 degrees of coverage because we don't have aftershock everywhere. And in this case, it's more like a line, but we can nevertheless feed a deeping layer, and that's actually a layer dipping about 20 degrees in the direction away from the San Andreas fault. So that kind of explains the bias and also correct the bias. And is this true? So we actually go into to look at the tomography models in the local area for Parkfield. And we find a cross-section where the array is located, and we see that if we zoom into the layers right beneath the array, there are some small angles dipping away from the fault. So I think this is a true problem. But after knowing this, we can correct it. And before the correction, that the estimate is about only kind of 5 kilometers. And if we do the calibration, it's 9 kilometers. It makes much more sense for magnitude 6. Again, that with just one array, we don't really see the whole picture of the earthquake. So with the single array, you see this is the 9 kilometers, and there are some kind of similar processing, but using all available stations around this region, then you get into this yellow estimate. It's slightly larger. If you look at finite fault solution, a more smoother solution, it's even longer. So it means that in order to get a more accurate estimate, we need to have multiple arrays covering different locations. But nevertheless, the order of magnitude for rupture length still makes sense for earthquake early warning. And another example we tried is the Mayor-Cupacah Earthquake. In this case, this is a strong motion array in the San Diego region. It's actually not very favorable location because it's not close to the faults and it's kind of oblique away from the fault trace. But nevertheless, that we can still get an estimate of the rupture size. But one single array again has some bias. It does see the rupture goes towards it a little bit longer than the rupture going away from it. But the overall estimate, 80 kilometers, is making sense for a magnitude 7.2 earthquake. And the last example I'm going to show is the Tohoku earthquake. This is not actually exactly for earthquake early warning because we're using the stations at the tips of the Japanese islands. But the idea is that if you scale this down, this example really shows that if you have multiple arrays, you will get a much better pictures. So what we use is the finite array, and we use the cluster in the northern tip of the Hokkaido island and the entire Kyushu island. So we estimate the back azimuth, then we intersect it to get different points at given time. And this is kind of the product of that, and the colors mapping the timing. So you really see that it starts from the hypocenter, then it goes down, and it goes up a little bit, then goes to the south. So it's actually image pretty good details of the rupture process, but in a much shorter time scale since we're using only the local stations. So that means in the future, if we have a design system along the active fault with multiple arrays, we'll be able to do this, and we don't need to assume the rupture trace, the fault length. And this example itself also demonstrates the potential to use this for tsunami warnings, because it's a kind of independent estimate on the rupture size and the rupture directivity instead of magnitude. And it's using local stations, you can get the results in the time scale of a few minutes. Okay, so that's what we can demonstrate at this point. And again, this is just a reminder that what are the settings we would like really to have. So multiple arrays covering overlapping field of view along active faults. Already there are a few presentations using GPS, using a seismic approach. So what's the point adding this additional array approach for earthquake early warning? Well, my take is that the array processing actually sees the high frequency perspective of the earthquake. So it's not necessarily the same as the low frequency. So I think it's adding an important complementary part to the big picture of earthquake early warning. And this is a finite fault solution from Shengji Wei, who's I think in the audience, where they were comparing the contributions of high frequency and low frequency. So on the left, this is the overall low frequency, and it's going to be dominated by the shallow slip close to the trench for Tohoku earthquake. But if you only see the slip with short rise times, you see actually the high frequencies. The short period is located at down dip. And if you compare the ground motion contributions from these two types the shallow sleep and deep sleep. So this is on the right is if you cut a few slices of the fault and you only compute the ground's motion contributions from the shallow sleep, it doesn't really contribute much to the real ground motions. And if you use the whole slip, adding the deep slip, you will see really the important high seismic intensities. So the idea is that for Tohoku earthquake, it's the deep short period sleep is responsible for the strong ground motions. So adding these high frequency aspect to earthquake early warning will be very beneficial in that aspect. And where I come from, the Los Angeles regions, you can see only the downtown area has high-rise buildings, and the majority of the areas is actually has only low storage buildings, 2 or 3 storage. So it's because the resonance frequency for this low storage building will be short period. So I think it's really the short period aspect of the earthquake means more to the ground motions. So so that's the argument or the rationale for adding high frequency or the array processing for earthquake early warning. So the conclusion is that we'll be able to actually demonstrate this array processing to earthquake early warning with a few earthquake examples, and we would like to have a network of a small-scale array near to the active faults. It's not exist yet, but we would like to have them. And this high-frequency aspect will be quite complementary to the low-frequency ground motion predictions. And in the future, we would probably even want to have high-frequency GMPEs, like the ground motion prediction equations, only for high frequencies. And that might be a good product, can be merged with earthquake early warning or the shake map itself. And we will also need to do a lot of more validation using more realistic examples like kinematic complicated ruptures with a realistic path effect, and also that's all. Thank you.
Okay, any quick questions here? Yeah.
Okay, so you have done now you have already say you can estimate the propagation direction. So for example, you have observed strong ground motions and the propagation direction. It is easy to predict future situation, not going back to fault geometry. So do you have an idea, in addition to going back to fault geometry, but also the forward prediction? I mean the strong ground motions here, propagation direction is estimated. So it is easy to predict next time six. So do you have some plan? Do you have some idea to include?
Sorry, what was the question again? Is
strong ground motion observed. So you estimate the propagation direction. So next time step, strong ground motion move here. We can easily predict.
Right. Yeah.
Do you have this is a forward method. So in addition, going back to focal geometry, but also the forward method, do you have some idea to include the forward technique?
Oh, so the question is, how would we include this information in the ground motion?
Yeah, I think this is one of the useful method for an ASCII early warning purpose. So
right. Yeah. But right now, what I can think is that if we see this rupture dimension, we stick into a forward model to make the ground motion predictions. But as I said, the high frequency might be a bit different from low frequencies. We will have to develop its own relationship for high frequency. Yeah.
And just a quick question. So
yes.
when you said these high frequency arrays, you mean like a kilometer and maybe 5 instruments, 10 instruments? I mean, what does it take to make a little array?
Right, yeah. So I think we don't need too many for this small scales. I think like a dozen would be enough. Even like 7 or a few of them. Yeah.
But is 3? Yeah. Can you do 3 sessions?
3 will be a little bit challenging because you will get a significant amount of aliasing. So
it'd be nice if they were cheap, a zillion of them.
Right, yeah. So that's kind of the idea that I didn't talk about. So you only need like maybe just a central station is a good station, then a few ones around it, then it can be much cheaper, and you can somehow maybe lower the cost of communication as well.
Okay, and any other questions? So just remember, we're reconvening at 1:30 to start the poster sessions, and there are talks again at 3 here. Okay.